The recent attention surrounding 3I/Atlas has grown significantly as astronomers continue to examine new data gathered during its passage through the inner solar system. One major contributor to this effort is the Survey System Atlas, short for Asteroid Terrestrial Impact Last Alert System, which, along with several other observatories, has played a foundational role in confirming data that strongly suggests interstellar objects like 3I/Atlas may be far more common visitors to our solar system than previously believed. Early studies of 3I/Atlas had already hinted at its unusual origin, but as the object traveled closer to the Sun, evidence became increasingly clear. Its glowing coma, a cloud of dust and gas formed around objects composed largely of volatile ices, expanded in brightness and size as solar heating intensified. This behavior, along with the emergence of other standard comet-like traits, left astronomers with almost no doubt that the mysterious traveler was a natural icy body originating beyond our planetary neighborhood. Despite this, some researchers remain cautious, noting that certain aspects of 3I/Atlas's activity stand out as especially interesting. While no one is yet claiming anything definitive, a handful of experts have pointed out that if additional, related behaviors were to appear in future observations, these patterns could potentially overlap with the kinds of anomalous signals that some might expect from objects of technological origin. This idea is not being proposed as a likely explanation, but rather as a scenario worth monitoring carefully, especially given the scientific debates that have already arisen in the wake of previous interstellar objects like 1I/Oumuamua. Since then, astronomers have become more attentive to subtle anomalies, wanting to ensure that every physical and dynamical clue is properly assessed. With 3I/Atlas, the question is not merely what it is doing now, but whether its future behavior will further solidify its natural identity or spark new scientific disagreement. Much of the most precise information currently available can be found in a detailed report produced by Davide Farnochia, a respected researcher at NASA's Jet Propulsion Laboratory. Farnochia specializes in orbital mechanics involving small bodies, with a particular focus on so-called non-gravitational perturbations, subtle forces acting on an object that cannot be accounted for by gravity alone. These perturbations are especially relevant when studying comets and other bodies that shed material as they heat up. Such forces can also play an important role in assessing which near-Earth objects could potentially become impact hazards. When applied to interstellar objects, this kind of analysis helps determine whether the behavior of a newly detected visitor conforms to what would be expected of a naturally formed comet, or whether something more unusual could be at play. One of the most essential parameters identified in Farnochia's analysis is the object's eccentricity, recorded at approximately E equals 6, 1373. This value is extraordinary, as eccentricities greater than 1 indicate open-ended orbits that are not gravitationally bound to the Sun. Most comets originating from the Oort cloud, a distant spherical shell of icy bodies surrounding the solar system, display eccentricities only slightly above 1, reflecting extremely elongated but still solar system originating paths. In contrast, 3I/Atlas's highly hyperbolic orbit far exceeds these typical values, marking it unmistakably as an interstellar interloper. Such a steep eccentricity not only confirms that the object arrived from beyond our solar system, but also ensures that it will never return once it exits, instead continuing on its endless trajectory through the galaxy. Another important milestone in the object's journey was its perihelion passage, the moment when it reached its closest point to the Sun, on October 29, 2025. At that time, 3I/Atlas came within about 1,356 astronomical units, a distance placing it just beyond Earth's orbital path. What made its arrival even more compelling was its retrograde inclination of roughly 175 degrees. This means the object approached from nearly the exact opposite direction of the planet's collective orbital motion around the Sun. Such a trajectory is incredibly rare for native solar system bodies and further reinforces the conclusion that this visitor was never part of our local planetary family. Instead, it entered our planetary region on a dramatic, steeply angled descent, a path shaped by its interstellar origins and the gravitational interplay it experienced as it approached the Sun. However, perhaps the most anticipated part of the object's approach involved the question of whether it would exhibit non-gravitational accelerations, tiny deviations from a purely gravitational orbit caused by internal activity, such as the outgassing of water vapor or other volatile substances. When comets heat up, sublimating ice jets can act like miniature thrusters, pushing the body slightly off its expected course. This phenomenon was famously controversial in the case of Oumuamua, whose non-gravitational acceleration lacked clear signs of outgassing, prompting speculation about whether its behavior could be explained by exotic natural processes or perhaps even artificial mechanisms. With that history in mind, astronomers were particularly attentive to whether 3I/Atlas would demonstrate any such measurable acceleration. As it neared the Sun Farnokias, findings confirmed precisely that 3I/Atlas did indeed display measurable non-gravitational accelerations, and unlike the baffling case of Oumuamua, the new data aligns well with typical cometary outgassing behavior. This strongly supports the hypothesis that 3I/Atlas is a conventional interstellar comet, composed of ices and dust similar to other long-period comets observed within our solar system. This discovery is remarkable because it provides scientists with another sample, only the third ever detected, of material formed around a completely different star system. Each interstellar object offers invaluable clues about the chemical compositions, thermal environments, and formation processes occurring in other planetary nurseries scattered throughout the Milky Way. Yet despite this reassuring evidence, not all experts are satisfied that the story is entirely straightforward. Some scientists have noted that the timing, direction, or strength of non-gravitational forces could still hold deeper implications. While outgassing remains the most plausible and widely accepted explanation, a few researchers argue that the pattern of acceleration deserves further scrutiny, especially if later observations reveal additional anomalies. They emphasize that extraordinary claims require extraordinary evidence, but they also stress the importance of staying open-minded when dealing with phenomena that emerge from beyond our solar system. Interstellar objects are fundamentally rare, and our scientific tools are still adapting to the challenge of analyzing bodies that only briefly pass through our observational reach. Because of this, even slight unexpected behaviors can raise important questions. Some scientists who adopt a more cautious view suggest that if 3I/Atlas were, hypothetically, to exhibit unusual changes in brightness, abrupt shifts in trajectory, or structural transformations not characteristic of known cometary physics, such phenomena could reopen discussions about whether a non-natural explanation might someday be warranted. These ideas are far from mainstream, but they reflect the intellectual curiosity that drives researchers to consider all possibilities, even those at the edges of conventional thinking. Interstellar objects inspire such speculation because they carry the potential to reveal entirely new physical processes, or, in the most extreme case, signs of artificial origin. Although this latter scenario remains exceedingly unlikely, it continues to motivate a careful, methodical approach to monitoring 3I/Atlas's behavior as it recedes from the Sun and moves back into the depths of space. For now, the current consensus leans strongly toward a natural explanation. The visible coma, the release of gas and dust under solar heating, and the match between observed acceleration and expected models all reinforce the classification of 3I/Atlas as a typical interstellar comet. However, the presence of differing interpretations among scientists underscores the importance of continued observation. As telescopes gather more data, researchers will refine orbital models, study light curves, and track how the comet's activity diminishes with distance. Each additional measurement contributes to a more complete understanding of what 3I/Atlas is and how it behaves. Ultimately, 3I/Atlas serves as both a scientific specimen and a reminder of how much we still have to learn about our galactic environment. Its behavior may be fully consistent with that of a natural comet, yet the fact that such objects continue to surprise us keeps the scientific community engaged and invested in exploring every detail. With improved detection systems and the growing sensitivity of astronomical surveys, future interstellar visitors will likely be identified earlier and studied even more thoroughly. For now, 3i/Atlas remains a compelling example of the complex interplay between data, interpretation, and curiosity, a traveler from another star system that challenges us to look deeper into the nature of the cosmos and our place within it.